name is Frank Sanders. I'm the head of the Telecommunications Theory Division at the Institute for Telecommunication Sciences, a laboratory of the National Telecommunications and Information Administration, NTIA, located in Boulder, Colorado. Over the past 30 years, we've developed a series of techniques for measuring emissions from various types of radio emitters. In particular, we've developed techniques for measuring emissions from radar transmitters. In this series of talks, I will begin by describing the fundamentals of RF measurement techniques, and I will culminate the series by describing our techniques for measuring emissions from radar systems, techniques that hopefully you can implement yourself. Accompanying this series of talks are notes available on our website and also NTIA reports that you may find useful. We hope that you will enjoy watching this series of videos as much as we've enjoyed producing them. Welcome to the 19th in the series of ITS RF measurement seminars. There will be 20 altogether, so this is the penultimate talk. The title of today's talk is Miscellaneous Spectrum Measurement Techniques, and we'll be looking at techniques for direction finding, amplitude probability distributions, and data that can be collected with a vector signal analyzer in the so-called modulation and phase domains. The first subject that I'll talk about will be direction finding. And the shorthand is in fact usually DFing, so direction finding. And I'm going to relatively briefly walk through these topics in this talk. This is somewhat of a survey. There are a lot of techniques for doing direction finding, making APDs, and VSA data in and of itself could be a long talk, but we'll cover these briefly. Direction finding tries to solve the problem of identifying the azimuth of origin of a radio signal, and I am at pains always to point out to people that when we're direction finding on a signal, we're not necessarily direction finding on the azimuth where the transmitter is located. We're direction finding on the azimuth where we're getting the strongest received signal from a transmitter. And I'll give a real-world example of a case where the two are not the same. It's usually assumed that they are the same. Right here in Boulder, we have our laboratory building located here at a given location on the Earth's surface. And to the west of us, we have a set of large rocks called the flatirons, which seen from above, we'll look at this as a map, where this is north. We have these rocks arranged, and in fact, if we look at the rocks from ground level or from the side, they sketch out looking roughly like this. They are something like 1,000 to 1,500 feet high. They're tilted back at an angle from vertical more or less like this. And so when we are experimenting with direction finding systems here at the lab, and we are sitting maybe right here with some kind of a radio receiving system, and we're looking for the direction of arrival of the strongest signal on a given frequency, we frequently find that our direction finding system is telling us that the direction of arrival of the strongest signal points back to somewhere along the flatirons. And we can, for example, do this with the local long-range air route surveillance radar. And when we do that, we do in fact find that we direction find on the strongest direction of arrival going right back into these flatirons, roughly west, maybe a little to the southwest of where we're sitting here. Now, it turns out that the location where the transmitter is located, where the long-range radar is actually located, is, for example, at Parker, Colorado, roughly 40 miles from where we're located here. And if we look in the true direction of the transmitter, we do see a weak signal being received in that direction, but on the frequency that long-range radars working at Parker, we see by far the strongest signal when we're looking in this direction. The reason, of course, is there is a ridge, which I'll draw like this. There's a big ridge that basically separates our lab from the location where the transmitter is located. It blocks, effectively, the direct path for the radio energy, but if you could stand on top of these 1,000-foot high or 15-foot high flat irons, rock formations, you would be able to see back to the location where that radar is located. These flat irons have a line of sight connection back to the location where this transmitter is located. The energy from this transmitter, which happens to move this way and has the right geometry to hit the flat irons at some angle of incidence relative to a normal to the flat irons, we'll call it theta, come off at the same angle, theta that way, propagates in, and sure enough we get a direction finding solution that points back to the flat irons. Now, this kind of thing doesn't necessarily happen a lot, but it does happen in urban environments where we have big buildings and skyscrapers in the vicinity. And it can happen in places, obviously, just as a cautionary note, you are direction finding on energy, you're not always necessarily direction. Enough said on that. Obviously, if we're ever trying to locate a transmitter, what we would do is direction find from more than one location and triangulate on it. So, given that we're trying to solve this problem of identifying the azimuth of origin of the strongest signal, what are the ways to do it? The most obvious way is to use a directional antenna, typically but not always, something like a dish antenna like this, where we use some sort of an antenna that is, for example, a log periodic. It could be any one of a number of types of antennas. We could also have a helical feed, etc. We mount it at the focal point of a parabolic dish, like so, and then use the parabolic dish to scan slowly around the horizon. And as we do that, we have the dish connected to a spectrum analyzer. So we'll set it up like this. Here's our dish. We run this into a spectrum analyzer or any other measurement system that can measure power as a function of time, because what we're going to do is, in fact, run a time trace like so, and we'll measure power as a function of time as we rotate the antenna 360 degrees around the horizon. And let's say that it takes 1 minute to do this, like so. And let's suppose that the signal that we're direction finding on stays on continuously. If it doesn't stay on continuously, we'll talk about that in a moment. So we start the trace here at time 0. We're going to run the trace for 60 seconds. And as the trace is running, we see our received signal. And in fact, we'll probably see something that looks a little bit like this. And down here at the bottom of the trace, we have the measurement system noise. Here, at this point on the trace, we have a point in time that corresponds to an azimuth in space where the dish antenna was in fact peaked up on the signal, and so we can correlate this time to an azimuth. This would say go from 0 to 360, so the way that I've drawn this would be at an angle of roughly, this would be 0 degrees, 180 degrees, 360 degrees, about 90 degrees. So this would be east, very straightforward. Now, what do we have over here? What are these features? Those features are the pattern of the dish. They're the antenna pattern of the dish. If the signal that we're looking for is strong enough, we'll actually illuminate the pattern of the dish as we're rotating. So we'll see the pattern of the dish as we turn the dish around. Now, if we do in fact have multipath scattering going on in our vicinity. We do have a building next to us. We have cars next to us. There are trees. There are fences. The real picture is probably going to be a little more complicated than what I've drawn here. What we're more likely to see then is something that looks like this pattern, but superimposed on the pattern we'll see the effects of the nearby reflective objects. So we may see a secondary peak here, we might see a peak here, we might see some kind of peak here. These represent energy from the transmitter which is being reflected off of, we'll say, in this case, a building, in this case maybe a fence, and in this case maybe another building. If you're not sure when you're direction finding about what you're seeing on a trace like this, and you're wondering what may be going on here, here's an easy way to solve the problem. Move the measurement system slightly from the location where you're currently sitting. If in fact these objects that I've drawn in red are generated by multipath, then if you go to another location close to the first location, but you move yourself, say, 100 feet or a couple hundred feet, what's going to happen is, if the transmitter is still located at a distance that is far away from you compared to the distances to the nearby multipath scattering objects, this is still going to give you a peak that's at about 90 degrees due east, and hopefully that is the strongest peak, although as I just said, it could be the Flatirons or some big rock formation, a big skyscraper. But the other multipath scatterers that are close to you are going to do two things. They're going to change in amplitude, and they're going to move somewhat in azimuth. So this one would move like that. This one might come in like this with a lower amplitude, and this one might actually develop a stronger amplitude, but again, it's going to move. So if you move slightly, multipath that's generated by things that are nearby is going to change on this picture, but the energy coming from the transmitter at a distance that is far away compared to these objects should remain nearly stationary. In a case like that, we might see this move a little bit like that with a slightly different azimuth, slightly different amplitude, but not much. And this could help to reinforce, when you're doing the measurement, the hypothesis that that is in fact the direction of arrival of the signal that's coming from whatever you're looking for. If you want to triangulate on the location for that transmitter, then you'll have to move a long distance from where you've started, a distance that is long enough to give you a substantially different direction of arrival from this direction of arrival at this location. The idea being that if the transmitter is located here at a point P, and you make your first measurement here at point number 1, and you direction find back this way, then when you go to location 2 and direction find back that way, you can triangulate. In reality, by the way, if you do this from more than 2 locations, you're not going to, in all likelihood, get the azimuths all crossing at a single point. What will happen instead is, when you go to, say, a third point over here, is you'll get a direction of arrival going that way. And so you'll wind up with a triangle, if you do 3 points, a triangle of uncertainty. If you do several points, this will begin to resolve itself into a sort of a polygon of uncertainty, depending upon how many points you take. And the most likely location for the transmitter is going to be somewhere near the center of the polygon. In order to further refine your search using a directional antenna like this, what you would probably want to do would be to come in closer and take another set of data points, say 0.4, 5, and 6, and now you'll have not this large polygon of uncertainty, but a relatively small polygon of uncertainty, and you'll rapidly home in on the actual location of the transmitter, hopefully. Now, I just described this with the assumption that the transmitter stays on continuously. What if the transmitter is turning itself on and off intermittently? That's more problematic, precisely because while you're trying to scan the dish around the horizon, the transmitter is turning itself on and off, so we could imagine that while the dish is scanning around the horizon, the transmitter turns on during this interval, and then turns itself off during this interval, on, off, and then turns itself back on during this interval. And now the problem is that if we happen to be aimed in the direction of the transmitter signal while the transmitter was off, we're really not going to see it. So instead we might begin to see the transmitter here as the dish began to come into it, like so. Then the transmitter turns itself off. It stays off. Here's the measurement system noise. It stays off. And then when by the time the transmitter turns itself back on again, we're looking nowhere near that azimuth. So we say, well, this is rather odd. Instead of illuminating the pattern of our dish, instead what we got was some gradual increase in energy, and then we got the sharp truncation. And if you see a sharp truncation like that, then it's a good clue that in fact the transmitter simply turned itself off at that point. The only way to get around this problem is to slow down the motion of the dish around the horizon, and in fact maybe even stop it at certain azimuths and wait for the transmitter to turn on while you're on certain azimuths, and graph in some data points like this over a period of many steps now around the horizon. We're talking about stop, wait, get an amplitude and the transmitter turns on, move the dish a little more, stop, wait. A much slower process, fill in. Oh, it seems to be something turning itself on and off with long off intervals. It becomes difficult to direction find on it. I will talk in a moment about a technique that we can use for the ultimate turn-on, turn-off transmitter, which is a radar, in which case we can build some specialized hardware with some specialized software and find it even though the thing is turning itself on and off 1,000 times, running a beam slowly through. That problem for the moment. Suppose that we need to run a mobile measurement operation. We're looking for a transmitter, and we really to basically move down a highway. Trying to put something on top of it around solution for a lot of reasons. And so what we really want in many cases, rather than a large antenna like this, is something small, some small kind of antenna that we can use for direction finding. And in that case, if we're trying to peak up on the maximum amplitude, we can go to a smaller, lighter weight antenna like this, which in principle can actually be held either in the back of a vehicle or out of a vehicular window, and can be rotated back and forth like this while we're actually mobile and moving down the road. Now, this is still not a terribly practical antenna to hold out the window, although I have done it. This, by the way, is a Yagi. This is an antenna that's made for a particular frequency, or for at least well, it's actually two antennas in one, but it's built to work on a small range of frequencies. We could just as easily do this with a wideband antenna, a log periodic array. But having said that, we'd like to go to an even smaller, lighter weight antenna, something that's extremely easy to hold out of the window of a moving vehicle or trying to drive down a highway and direction find on a signal. And basically the smallest, lightest weight antenna we can imagine, and one which has almost no wind loading when we're trying to hold it out of an antenna, out of a window, is in fact a dipole. And we'll assume that what we would build would be a half-wave dipole antenna. Dipoles, in terms of the direction finding technique that I'm going to mention, in terms of construction, are practical for frequencies up to about a gigahertz. They become somewhat impractical frequencies above a gigahertz because the physical size of the antennas becomes really small. At a gigahertz, a half-wave dipole is roughly about this big. Going much smaller than that is just not practical or feasible. But since a lot of the time the signals that people need to direction find on are land mobile radio signals or aeronautical mobile or other types of mobile radio signals which are not found at frequencies above 1,000 megahertz, a dipole is not a bad measurement solution. But the dipole is not a particularly directional antenna. The dipole antenna pattern, of course, looks basically like this. Here's our dipole. And the pattern, seen either from above or from the sides, has this appearance, like so. The gain of a dipole on either side is about 2.1 dB above isotropic, and it's clearly hopeless, fairly hopeless, to try to direction find using that broad beam. So we don't. what we do instead is, rather than peaking up on a signal, the way we would with the dish antenna, to find the strongest signal strength that we can obtain, what we do instead is use the null off either end of the dipole to minimize the received signal strength, like so. So the trick here is to minimize received signal strength. And the technique is still the same. In terms of how we use the spectrum analyzer, what we'll do is, I'll just go to the next board. What we'll do is assume that we are going to operate a mobile direction finding operation. And in the mobile direction finding operation, we're going to set up a vehicle, and the vehicle will be some sort of a sedan like this, not a particularly practical one. I'll draw the wheels slightly larger. There we go. And we're going to have a driver and a measurement person, and someone is literally, and I have actually done this, is literally going to hold their arm out the window, like so, and hold on to a dipole antenna, like so. And inside the vehicle, we connect the dipole into a spectrum analyzer. And now, we'll probably want to go ahead and set the spectrum analyzer up for something like a 5-minute sweep time in a 0 hertz span on the frequency, of course, of the signal that we're trying to DF on. And then we start running a data trace on the spectrum analyzer. And as the vehicle is moving down the highway, you simply rotate the antenna back and forth while you watch the spectrum analyzer display. And obviously, the person who's doing this needs to not be the driver. And what you're going to see will be the signal on a frequency. And as you turn the dipole, you dip it down, and now you turn the dipole and it comes back up, and turn the dipole more and it comes down, turn the dipole more, it comes up, turn the dipole back and forth, and you simply note the direction that the dipole is itself turned on whenever you're able to null the signal out, like so. And now, that direction has to be either, well, that axis identifies the axis on which the signal lies. And in this particular case, we'll say that as we're driving down the highway, we're finding that this, and I'll draw it like this, here's the highway, we're moving along the highway like this, and as we go, we find that whenever we have the dipole oriented this way, null, 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 here's null 1, 2, 3, here's null 1, 2, 3, we say, ah, well, that's it then. The signal nulls when the dipole is held at this angle relative to the car, relative to the highway. And what we now know is the signal is either in this direction or the signal's in that direction. We don't know which. If we were to modify the dipole such that we only had one null off the end, then we could resolve that ambiguity. Otherwise, what you have to do to resolve the ambiguity is either drive far enough along the highway that you begin to get a change in the azimuth to the signal, like that, in which case we know that the actual direction of the signal must have been that way, or we actually turn a corner, drive onto a second road, which maybe, for example, goes like this, and and then start direction finding as we're going along that highway. But the technique is very, very simple, very lightweight, very easy to implement, and I've personally used this with excellent results, and I like it for its simplicity and robustness. Now, if the signal itself is turning on and off while we're trying to direction find, then what will happen is the trace that I just drew will be modified like this. If the signal were to turn off right here, it would drop out like that, and then when the signal turned back on, it would come up like that. And then if the signal were to drop out here, we'd see this happen, and then the signal would come back on. And the trick is to recognize that the signal is turning itself on and off, and we know when the signal is turning itself on and off because we're going to get these abrupt cutoffs where we get a sharp angle. We see the signal power drop instantaneously and come back up again. That's not likely to be due to encountering terrain or multipath. That's almost certainly due to the fact that the signal's turning itself on and off. So, relatively easy, I think, to tell the difference between the signal turning itself on and off versus the nulls that we get as we're physically rotating or turning a dipole from side to side. Now, suppose, however, that we're not looking at signals that are land mobile radio type signals, or even digital communication signals which have fairly high duty cycles. Suppose that we're looking at the problem of direction finding on a radar. Now, we've talked enough about radars to know that a typical set of radar pulses graphed in time, here's received power, will look as follows. We'll see nothing while the radar beam is not aimed in our direction, or else we'll see very low amplitude, which is from the side lobes of the radar antenna. And then as the radar beam begins to look in our direction, we'll see a set of 10 to 20 pulses like this, and 10 to 20 pulses, and we'll see this kind of behavior happen every few seconds as the radar beam sweeps over our position. And for typical air search radars, the pulse repetition interval will be something on the order of a millisecond. The pulse width will be something on the order of a microsecond. And that's for air search. And if we're looking for signals from an X-band maritime radar, we're going to see pulse repetition intervals that are more on the order of say 1 microsecond, and we're going to see pulse widths that are on the order of something more like 50 nanoseconds. Maritime navigation, surface search type radars. The problem with trying to direction find on these kinds of signals by peaking up with a dish antenna, or by, well, first of all, the dipole won't work because these are microwave frequencies, so that's out. Other similar types of systems won't work, including dish antennas, because any scheme here that is based on a mechanical rotation of an antenna around the horizon is going to suffer from the fact that if we're getting a good direction finding solution by peaking up on the signal, we're going to be using an antenna to direction find, which is going to have something like about a 1 degree beam width. This is the direction finding antenna. And in order to effectively direction find on a radar, we're going to have to actually move this antenna to a particular azimuth here. Then we're going to have to stop the rotation of the DF antenna. And then we're going to have to wait for this interval, the beam scan interval of the radar, which for an air search radar may be, for example, 5 seconds, and for a maritime surface search radar might be more like 2 seconds. Get an amplitude for receive power on that azimuth, and then move this antenna, the direction finding antenna, by 1 beam width like that. which is 1 degree. So this is the next azimuth. And take that data point, and so we're only going to be able to move, in this particular case, 1 degree per, let's say, 5 seconds. And in order to scan 360 degrees around the horizon at 1 degree every 5 seconds will require 360 times 5 seconds, which is more time than we want to take to find a radar for 2 reasons. We have a limited amount of time typically to work at field sites. Second reason is not all radars are going to stay on or stay present in the area long enough to be able to get an effective direction find on them before the radar itself moves away. For example, maritime radars are mobile. We also have the problem of aeronautical radars. They're mobile. We also have the problem, well, of any mobile radar. And so we need to get direction finding solutions on radars in something more like a few seconds, both to minimize the measurement time that we're expending in the field and also to get a good direction find on the radar before it either moves out of the area or for some other reason becomes unavailable to measure. For example, it could just be turned off. So how can we do it? The way that we do it is to build, instead of a high gain dish antenna, although and I should say there are spinning dish direction finding systems that are available. Their efficiency and efficacy is not necessarily always everything that you might desire. But what we do instead is we build an array of low gain antennas, cavity back spirals, and we're going to use this array with a fast electronic switch to do the direction finding instead. Here's the principle of the thing. A single cavity backed antenna like this has the characteristics of about a 90-degree angle between the 3 dB points in the antenna pattern. So here's 3 dB. And I'm going to draw the antenna pattern here. Here are the 3 dB points. And I'm going to draw the antenna pattern in terms of antenna gain or response as a function of angle. And this is going to represent an angle, ideally, a total of about 90 degrees. And then this antenna pattern comes down like this. And then we have side lobes coming off on either side, like so. And what we are going to do is now set up an array of these antennas. And here we have an array that we've been building here at the lab. This particular array happens to have 6 sides on it, 6 sets of cavity back spirals, and on each face of the array we have a low-frequency cavity-back spiral that goes from 1 to 8 gigahertz, and then a high-frequency cavity-back spiral antenna that goes from 8 to 18 gigahertz, so we have a total direction-finding capability here of 1 to 18 gigahertz. This array won't work for signals below a gigahertz, but most radar systems operate above 1,000 megahertz, 1 gigahertz. There are some radars that operate at lower frequencies, but the bulk of radars are in the microwave part of the spectrum.
Now, are these switched?
Now,
one antenna set
yes. I'm going to explain the details in a moment, but inside the array, as we can see here, we have some electronic switches that allow us to rapidly switch from one antenna to the next as an input into a receiver. What's the principle? The principle is this. Given that we have one antenna located in the array here with a 90-degree beam angle, so this is 45 degrees, we put a second antenna into the array at a 60-degree angle away from that, like so. I'm drawing the array as seen from above, rather crudely I might add. This is supposed to be a hexagon, all right. Like so. This is the array seen from above. Array from above. Okay, so we have one cavity back spiral built into the array on this side. We'll say that that's this antenna. In fact, I'll draw it in black just to make it easy. Okay. Now, we're going to put a second antenna into the array over here, and this one will draw in green, like so. Angularly, it's set off at a 60-degree angle from the first antenna. So we take this pattern and we move this pattern 60 degrees off, and 60 degrees off is going to put us, let's see, this is 45 and that's 45 because it's a total of 90 across. So we're going to move 45, 55, 60. We're going to have another one over here about like this. Try to draw it somewhat carefully here. Coming down like that. And again, it's going to have side lobes, like so. Like so. And the, let's see, 60 degrees. I want to make sure I drew this properly. Yeah, that's a 60, right, that's a 60-degree offset. So the offset between these two centers is, I may have actually drawn this wrong. If I did, I'll correct it. Okay, the offset between these two centers is 60 degrees. There's 45. I think
90, that's way too big.
It's too big, sorry. Excuse me, I'll get it right. Excuse me. Yeah, that's 45, and that's 90. Excuse me. I will fix that. 60 degrees is, it's about that much. Okay, there's a 60-degree offset, and that puts, yeah, actually that makes more sense anyway. So I'll redraw the pattern here. We'll get it right. All right, draw it like this. Yeah, like so. Except I'll draw it in green. Okay, here we go. Green, down. Side lobes like so. Okay, so 60-degree offset. Just draw it like that. 60-degree offset between these. Like so. So the 60-degree offset I've drawn here is that 60-degree angle there. 90 degrees on each of the antennas. And the technique that we use is to try to measure the radar pulses as they're sweeping across our location on both this first antenna number 1 and this first and the second antenna number 2, like so. So here's antenna number 1, here's antenna number 2, like so. Take that off. Now, if a radar is located in this direction, let's make it really easy. Let's assume, first of all, that the radar happens to be located exactly halfway angularly between antennas number 1 and 2. If that's the case, then the radar emission, I'm going to go ahead and erase this part up in here. If that's the case, then the radar emission is going to come in like this. And if we can make a measurement of the radar emission on the first antenna and the second antenna, while the radar beam is in fact scanning itself across our array, while it's scanning across our location, we're going to get a data point back from this antenna that'll be some number like minus 46.2 dBm, and we'll get a measurement from the second antenna that'll be virtually the same, say minus 46 dBm. And by virtue of the fact that we're measuring the same power on these two adjacent antennas, we know that the direction of arrival of the radar has to be halfway in between. Now, in order to know that the direction of arrival really was between these two antennas, we have to not only take a measurement on these two antennas while the beam is sweeping over our location, we have to, in fact, take a measurement on all 6 of the antennas while the radar beam is sweeping across our location. Now, this comes back to the characteristics of the radars that we're trying to measure. What we want to do is get a measurement on a group of radar pulses that are almost equal in amplitude to each other. And when I drew this just now, I drew it a little bit, maybe misleadingly. When I say 10 to 20 pulses, most radars put out 10 to 20 pulses between the 3 dB points of the radar's antenna beam. You remember that's how the radar works. That's the whole trick to building a successful radar. You get 10 to 20 pulses that are all within 3 dB of each other, such that you're able to integrate the returns from those 10 to 20 pulses to develop a received target indication in the receiver. So what we need to do with this array is scan the array and take 1, 2, 3, 1, 2, 3, 4, 5, 6 data points, one data point on each of the antennas within the interval that the radar takes to move its antenna across our location between its 3 dB points. And so to take the case of the air search radar, how long is that? Air search radar. Well, 1 millisecond between pulses, pulse repetition interval, and we'll go worst case scenario, we'll say that it's generating 10 pulses in that interval. That's 10 milliseconds. So for this air search radar example, we have to get 6 data points in 10 milliseconds. So we have to 6 points in 10 milliseconds. And so I'll invert that. We have to get, well, in fact, we'll make it and just make the math easy. Make it 12 milliseconds just to make the math easy. So now we get 1 point every 2 milliseconds. So that's how fast, roughly, we have to switch this array. Now, if we have a radar that has a pulse repetition interval that is a fraction of this, we're going to have to scan the array itself commensurately faster. There's no way to do that with a mechanical switch, so instead we use electronic pin switching to switch the array, to switch these array elements rapidly. But if we do switch the array elements rapidly, we can keep doing measurements continuously, taking each antenna every 2 milliseconds, and we run this array at this data rate, taking a power measurement off of each antenna every couple of milliseconds for a period of 1, 2, 3, 4, 5, etc., until we get to the point in time when the radar scans across our location. Most radars will look in our direction within 10 to 12 seconds. So we have to keep up this sampling for up to about 10 or 12 seconds if we're looking for a radar on a frequency. And as we're doing this, we actually load a data array, 1, 2, 3, 4, 5, 6, for the 6 antennas, and then the depth, the height, the depth of this array goes down for every rotation that the pin switch does around the array. So we get a set of data points which are minus 100, minus 100, minus 100, etc. When we're not seeing the radar, minus 100, minus 100, minus 100, minus 100, minus 100, minus 100. We keep doing this over and over and over again until finally, at some interval of a few seconds, we get a set of array elements which look more like minus, and I'm going to copy what I did here, minus 46 on antenna number 1, minus 46 on antenna number 2, minus 60 on antenna number 3, minus 65 on antenna number 4, minus, say, 75 on antenna number 5, and then back down to minus 90 on antenna number 6. So looking at that array, we say, the radar just scanned over our location, and in order to localize the radar's position, we first of all find the 2 adjacent antenna readings that gave us the 2 highest power readings. Hopefully they're adjacent. I have seen cases where they weren't adjacent, where this one and this one, for example, gave the highest power readings, and that's a bad solution. In that case, we have to wait for the radar to come around, and we'll get it a second time. But assuming that we get 2 adjacent antennas that have the 2 highest power readings out of the 6, we then calculate the direction of arrival of the signal by comparing the strengths of those two readings off those two antennas. Now, the case I just did is a very, very simple case. It's one where we got the same reading on the two adjacent antennas, and there obviously we can split the difference on the two. We know that this had to be the direction of arrival going out this way. If the two power levels are not equal, let's suppose that the two power levels differ from each other by 6 dB. We'll say that this power level on antenna number 2 was the highest, and that the power level on antenna number 1 was 6 dB lower. Easy. All we have to do is find the point between the two patterns where the difference between the two antenna patterns is 6 dB, and where antenna 2 happens to be the higher of the two patterns. And we then come down here and simply, in software, read off that azimuth. Now, this direction finding technique relies upon knowing not only what the patterns of the cavity back spirals are, but upon knowing what the patterns of the cavity back spirals are when they're built into this kind of a housing, and which may itself be sitting on top of a tower, which may be sitting on a vehicle. And for this, we can actually take this housing out to an antenna range, and we can characterize the antenna patterns of each of these 6 antennas, hopefully they're all the same in the array, on an antenna range. And having characterized those and having graphed those out into a data array in a computer, then it becomes a simple matter of doing a lookup where anytime you see power coming in from the two adjacent antennas with some difference between 0 to, and I'll come to this in a moment, some larger number of dB, you simply find the point where that power difference occurs between the two patterns when you've picked up a signal and you say, ah, we've got it. Now, the problem that can occur with this is that we can get into an ambiguity. And the ambiguity occurs here. If the difference in power received between the two antennas is sufficiently large that we get a solution, I'll get rid of these extraneous lines, sufficiently large that we get a solution which gives us a, which gives us a delta, here's the delta, like that. We'll say, for the sake of argument, that this is 12 dB difference. The problem we have is that there's not a single azimuth where we get a 12 dB difference between these two patterns. We get a 12 dB difference here, but we also get a 12 dB difference. This one's coming down. We get a 12 dB difference here, like so. There's 12 dB again, and so forth. The problem is that these antennas do have side lobes. So if we get into this situation, where the power difference between two adjacent antennas is large enough to put us into the ambiguity region on the solution due to the side lobes of the antennas, then we're not able to assign the radar to any particular azimuth. And in the past, when I've had to deal with this, I provide a default that says that the radar is somewhere on antenna number 2. In this case, it's somewhere in this quadrant, but we basically leave it at that. We could even say that it's in this quadrant, but it's probably shifted over. Well, but it's shifted over to this side. But we don't get a very good solution. In fact, it's kind of funny that, in other words, we don't want to get too large a power difference between any two adjacent antennas in the array. We actually want the power difference to be small enough that we don't get into this ambiguity. Now, we can minimize the problem with the ambiguity by trying to keep the side lobe energy, the side lobe levels, as low as possible, obviously, from one to the next. Ideally, there would be no side lobes, and if there are no side lobes, then this wouldn't have any ambiguous angle of arrival. But that is the basic technique for building a relatively easy radar direction finding capability, and it really hinges, other than the other than the hardware that you have seen here, on writing software that will process these data points rapidly, and on having available electronic pin switches that can switch the array fast enough to sample all 6 antennas in the array within the time interval that a radar beam will require to scan across your position. And that, of course, depends on the kinds of radars that we're looking for. One side note or trivia note, if you ever go on a harbor cruise somewhere and you look at Navy ships in any of the world's navies, you will typically, on a variety of the vessels that you'll see in port, see bumps on the side of the ship that are 3 sides of a hexagonal array. And what's going on there, of course, is that they've mounted an array like this on the ship, but they put 3 sides of the array on one side of the ship and the other 3 sides of the array on the opposite side of the ship. So that indicates that there's a direction finding capability on board. And as I say, you can see that with pretty much, with ships in pretty much any of the world's navies. And in fact, you'll often see two of these arrays. You'll see 3 sides that are really large on the side of the ship, and then you'll see a smaller one replicated above it. And what they're doing there is operating just like we are with 2 octaves, except instead of building the antennas into one flat panel, they've got 1 panels for the big cavity back spirals and another smaller set of panels above it for the small set of cavity back spirals for the higher frequencies. But it's a very straightforward direction finding technique. So, any comments on that? All right. Next, amplitude probability distributions. I'm going to cover these quickly, and the reason that I'm going to talk about them, APDs, amplitude, probability, is that they're not always, APDs aren't always covered, I think, in coursework. Amplitude probability distribution, and the reason they're not always covered I'll come to in a moment. But first I'll describe what an amplitude probability distribution is. An amplitude probability distribution is nothing more than a graph, set of data points, that shows voltage, or we can convert it to power, and it's really a voltage threshold, graphed as a function of the percentage of time that energy, because it may or may not be a signal, in fact it's typically noise, but not always, typically noise, not always, exceeds the voltage. And the typical way to graph this out is, in fact, to render the voltage into decibel units of power, which means that this is a log plot versus the log of the percent of time that the signal or the energy or the noise is exceeding the threshold. Now, why, you might ask, why would a person want to do this? The reason is that although many radio systems, maybe most radio systems today, are built with the assumption that the radio receiver is going to have to work in an environment that is limited by Gaussian noise, in fact it may often be limited by thermal KTB noise, which is inside the receiver circuitry, which, by the way, on this kind of a plot, as I've just drawn it, will produce a straight line Gaussian noise, and this will have a slope of -1 on this plot, and this could, for example, be KTB noise, thermal noise. Although many radio systems today are designed with the assumption that the radio is going to actually work against Gaussian noise, in which case it turns out we don't really need an APD, there are cases in which non-Gaussian noise occurs in an environment, and you cannot necessarily, in fact you usually cannot at all, gauge the performance of a radio receiver in a non-Gaussian noise environment simply by measuring the average power in the non-Gaussian noise. The reason is that the non-Gaussian noise is going to be somehow clumpy in time. Basically, for example, it could be pulsed. You get a high pulse of energy, then you get nothing, then you get a high pulse of energy, then you get nothing, then a high pulse of energy, and then nothing. If a radio receiver is trying to work in that kind of environment, that is a non-Gaussian noise environment. And simply taking the mean power on non-Gaussian noise will not tell you how the receiver is going to behave, basically because the noise energy is coming in some sort of a distribution that's somehow clumping itself up, I'll say pulsing itself. And the statistics that we need to assess the radio's performance then can be, in fact often have to be, obtained from an amplitude probability distribution. So, basically, first I'll show how we get it, which is dead simple, and then I'll show what a typical non-Gaussian noise or energy distribution might look like. To get the APD data, we're going to go back to working in time, and we're going to measure power. Power is a function of time, and we're going to see something like this happening. I'm drawing non-Gaussian noise here. By the way, although unintentional man-made emissions can produce this kind of noise, other sources of non-Gaussian noise include lightning, and this is a problem down at lower radio frequencies. Back in the old days, it was a problem down in the AM radio band, but lightning, ultra-wideband transmitters, and I'll just say etc., can produce non-Gaussian noise. So if we're so in the old days, people were worried about building systems that might encounter noise from lightning. Nowadays, people might be worried about building receivers that are going to have to work in an ultra-wideband transmitter noise environment. In either case, we're going to want to get the statistics on the time waveform, and what we do is sample the time waveform like so. Very simple, dead simple. We need to sample it long enough to make sure that we're getting a good representative set of data points in here. And then, all we do, using software, is to produce this set of thresholds, and it's really nothing more than a sorting problem. We sort all of the points that we took through some interval of time, and we simply plot the percentage of all the points that we took over some interval of time in terms of their power level versus the, now here, percentage of time is same as percentage of points that exceeded some given power level. So for example, we have basically one point in this whole array that hit this nice high power level. So we have 1 point up in here, and then as we come down, we don't have too many points up here at these higher power levels. We've got one here, we keep on coming down. Oh, there's one, there are two, there are three. So now we have a lower power level, but more points exceeding that power level. So we get something that looks like this. And as we graph this thing out for the non-Gaussian noise, we're going to get a curve that looks typically like that. Now, what's this part of the curve? This is the part of the curve that we would get from ordinary KTB thermal noise. This part of this non-Gaussian curve is our measurement system noise down here, which is thermal noise. So eventually, we're going to drop down into this region where we're seeing the thermal noise in our measurement system. But up here, we're seeing the effects of the source, the lightning, the ultra-wideband, whatever it might be. And we can actually use some particular points in this graph. I'm going to graph this is 37%, say this is 50%. And just refer to my notes, make sure I get this right. Yeah, so here at about 37%, we have average. We have average power. We can also graph average volts. We can also graph median power, 50%, and so forth. But the beautiful thing about these, and we can do the same thing for the non-Gaussian, the beautiful thing about this is that with the APD we can see what this behavior, what this characteristic looks like, and at NTIA, we've used these data graphs extensively in analyses of the performance of receivers in the presence of emissions from ultra-wideband transmitters. And I think I'll leave that discussion at that, just to point out that this is a tool that is available. It's relatively easy to get the data graphs, and a person could go through their entire career and never have to work with this, but if a person is ever working in a non-Gaussian noise environment that may degrade the performance of a receiver, it's worth knowing that APDs exist and that they are needed to get this. One last thing I do want to say. If you have an APD graph like this, you cannot go backward to reconstruct this time diagram. For example, if we had a set of pulses coming through here that were, let's say, 1 millisecond apart, we cannot get the 1 millisecond pulse spacing off the APD. For that, we have to go back to the original time data that we collected to see what the spacing is. So this gives us the APD gives us a nice statistical picture of noise, but it does not allow us as such to go backward to what the noise looked like. If you want to go backward to what the noise looked like, be able to actually see, for example, the spacings between these pulses in time, you will need to retain the original noise data if you're doing that with an APD. The last topic, and I'm just going to really touch on it briefly here, are data that we can take from a time sampling machine, a vector signal analyzer, and which we here at ITS have used typically on radars, but can also be used on digital data signals, vector signal analyzer data. I just want to, and I really will cover these really briefly. First of all, we have the modulation domain. Modulation domain information shows the frequency of a signal as a function of time. And for example, for a chirped radar pulse will actually look like this, and then drop off, and then we see noise. This would be a radar pulse that turns on at some point in time, has a frequency that varies linearly through time, and then turns itself off. This is measurement system noise on either side. And there are systems that are linear frequency modulated, which will look like some sort of a sawtooth or ramp. And if we're looking at a nonlinear FM modulation, it will in fact look something like that. These can also be used for, well, they can be used for any frequency modulated signal, basically. I'll leave it at that. Secondly, phase domain. And in phase domain on the vector signal analyzer, we generate a picture which likewise shows phase as a function of time. This can be used with digital data systems, digital data signals, and again radar pulses, and others as well, but these are two major applications. And again, what we'll see is measurement system noise. Then coming out of the noise, we see a change in phase, and then if we're looking at pulses, either some sort of digital data turning on and off, or else we're looking at a radar pulse, the system will terminate itself, we're back down into the noise. And with this data in hand, we can analyze either of these two types of signals. And although that's brief, I'll just leave it at that unless there are any particular questions. I just want people to be aware that we do have these capabilities available in VSAs, and that they are useful for looking both at modulated radar pulses and digital data signals typically, but not always. That's it. I was watching Bill's fingers thinking, okay, I got it. I didn't want to go into tape number 2. Didn't want to go into tape number 2. So, kind of a brief survey, but at least now you know what the.
I was going to comment, but I kept it off.
Yeah, there we go.
The APD construction sort of a